Chung, who will tell us about the black box simulation barrier persists in a fully quantum world.
Yeah. Just to make sure that I can talk until 3:20, right? You earned it earlier 10 minutes. Okay, sure, still 40 minutes. Sure. Um, yeah, thank Domiyuki for hosting this nice event. Today I'm going to talk about the lower bound for fully black box zero knowledge. This is joint work with Naihui Jia, Kaimin Zhong, who's in the audience. If you want to take a nap, this is the moment. And also Jiahui Liu. Hey, let me start. Um, I don't need to recall the definition of zero knowledge. You all are experts. So one thing I do want to emphasize is that you can think the interaction between the prover and the verifier as like the verifier trying to ask the questions and the verifier trying to give answers like round by round, very roughly. And only the one who holds the real witness can answer every question correctly. Eventually, the verifier will decide to accept or not. So as you know, if you just have companies and some requirement, this is the same as the like maybe not IP, but interactive arguments. So what makes it interesting for cryptographers is the zero knowledge property that we learn nothing. And as you all know, we capture the informal intuition by something called the simulation paradigm. And we imagine the real world, that's where the real execution happens, and the simulated world where there is a simulator without knowing the witness. So we say zero knowledge is fulfilled if the verifier basically learn the same thing in the simulated world as in the real world. So in this simulated world, I want to draw the picture in a slightly different way as you've been seeing before. So you can think that still the verifier is keep asking questions to the simulator. Since the simulator doesn't have the real witness, so he could get stuck at a certain point. But the advantage of the simulator over the prover, honest prover, is that the simulator can do something like rewinding. So he could rewind the execution back to a previous point to ask for, like, to enforce the verifier to give a new question. Maybe the new question is like he's still unable to answer. He could keep doing so until like attempt that it hits the question that the simulator is able to answer. Then we can like get rid of this round. But still, there are like other rounds. However, you can keep repeating this rewinding strategy until the end of the execution. That's like another way to view. I mean, this is another way to draw the what we call rewinding. If you draw it in this way, it becomes clear that for every rewinding, you need a copy of the verifier. Now, classically, somehow we didn't draw the picture in this way. We think that, okay, it's a single machine. You can just rewind it back. But if you think it more carefully, you are actually requiring a new copy. You can think that once the execution gets stuck, you just need to start a new machine. If you think it this way, it's obvious that you cannot do this in quantum setting because a malicious verifier could have its own like quantum private state so that you cannot clone. So that's why like basically the whole theory of zero knowledge requires a new require us to like, re-establish the whole like theory of quantum zero knowledge in the quantum setting. So this is like a large area of research. Today, I'm particularly interested in the lower bounds for zero knowledge. So basically, we are trying to characterize like under which conditions we can do zero knowledge. This is like large area of research, like even traditionally in the classical setting. So if we take a like a uniform like a perspective of this line of research, as I explained before, the only advantage of the simulator seems come from its ability of rewinding compared with a malicious verifier. Sorry, with the honest verifier or malicious verifier. So if you want to like prove like impossibilities, basically you need to identify conditions under which the advantage of rewinding goes away. So if you view it in this way, this is the list of important major lower bounds for like zero knowledge. The first such lower bound was established as early as like 1980s, almost like probably 3 or 4 years after the proposal of the concept of zero knowledge. People quickly realized that if you just have one round, zero knowledge is impossible. That's because if there's one round, you don't even have any opportunity to rewind the execution. Like this is the easy setting you can think of, like where how do you like invalidate usefulness of rewinding. Why 1988? Because this is the year like Bloom, Feldman, and Micheli published a paper of non-interactive zero knowledge. And at that moment, they realized that, okay, you need something extra, CRS or random oracle, something extra set up. Yeah. Which one you are asking about, talking about?
There's a paper at Fox that does one round zero knowledge.
Is that one like a considered different model? You basically, okay, you are kidding?
Sorry?
Are you serious? Like,
No, yeah. I mean, why doesn't that contradict what you said?
We have to be like more specific about the conditions. For example, I'm here talking about black box zero knowledge.
I see.
If you allow like non-black box technique or your change of your like logical system, then that's a different story.
I see.
Yeah.
Thanks.
So maybe I should emphasize that here. You see, I'm emphasizing black box zero knowledge where the simulator makes black box access to the verifier. In this setting, like a standard setting, you can say that only advantage of the verifier seems to come from the ability of rewinding. So if you somehow remove the power of rewinding, then you shouldn't have zero knowledge. Okay. Then later, like the work of Godrak and Kahan, they established the impossibility for 3 rounds or public coin, but any constant rounds. So later in 2002, Barak Lindahl basically established the impossibility for any constant round, removing the condition of public coin requirement. And this is considered as like a combination of the classical impossibility results. Then, since we are here for like quantum cryptography, we are most interested in the quantum setting. So the first setting to consider in the quantum setting is something called post-quantum. I believe all of you know that. In this in the knowledge setting, it means particularly that honest parties are classical, including the channels. But the adversary, if you are talking about soundness, it's a malicious prover. If you are talking about ZK, it's a malicious verifier. The adversary could be quantum. So we are focusing only on ZK. I want to emphasize that if the verifier is quantum, your simulator should better be quantum as well. Otherwise, you cannot utilize the full power of the quantum verifier for your simulation. So in this setting, CCLY 21 established the.
I guess some of these results, like here you're talking about strict polynomial time simulation.
Yeah.
Because some of these results also apply for expected polynomial time simulation, right? That like Barrett Lendl doesn't, but like some of the other.
Yeah, you're right. And that's basically that's one of the major message conveyed by CCLY 21. They established that in the post-quantum setting, this impossibility also extends to notion of expected quantum polynomial time. This is something like I deliberately want to hide from this talk because there are too many techniques I want to talk about. Yeah, you're right. I think you are the expert. Of course, you also have the notion of expected coherent running time. Yeah, I want to avoid that discussion.
Okay, we just want to think, I guess, just to help me. We just think about like strict polynomial time.
Yeah.
Thank you.
Yeah, the most simple thing. Yeah. So where was I? Yeah, I was saying that CCLY 21 established a lower bound in the post-quantum setting. However, if you think about this, like this is not really the end of story because the post-quantum setting you are restricting the honest party's power. However, you allow the asymmetry between the honest party and the malicious guy. The malicious guy can use full quantum power, right? So I would say the most ideal result would be like so what we call fully quantum setting, meaning that all parties are quantum, both the good guy and bad guys. And in this setting, like, will anything change, or can you like bypass the post-quantum lower bound, or does it still apply? Moreover, as like our talks like for the past few days, we also focus a lot on the LLCC model. So you can ask the same question, like for the LLCC model, does the post-quantum lower bound still hold? So today, like I'm going to show you our results that basically we prove that the same lower bounds holds even in the fully quantum setting. And our result also implies the impossibility for the LCC setting because in fully quantum setting, honest parties are allowed to use quantum channel. If you can still do zero knowledge, then of course you cannot do that in LCC setting as well. I'm just saying that without answering the fully quantum setting, we don't even know nothing. We don't even know much about LCC setting as well. Yeah. Okay. So if we zoom into the last recent 3 results, I want to emphasize that the implication of our results is first, our results explains why existing quantum zero knowledge and even quantum multi-party computation requires either super polynomial constructs or non-black-box simulation. So given the CCLY21, you can see that if a post-quantum protocol achieves the construct, then it has to use non-black-box simulation. But it doesn't say anything about fully quantum setting. For example, if you have a ZK for QMA, probably you must need quantum communication because the witness is quantum. Or we have the notion quantum multi-party computation where you compute a quantum functionality. In those constructions, the best known construction, all of them utilize quantum communication, and they have either super construct or using non-black-box simulation. This situation requires an explanation. If you just have CCLY, it doesn't suffice to explain that situation. But now we have this CCLL24. It explains the situation. This is something necessary. Okay. Next point is for the previous results, you can at most connect your knowledge with the computational class of BQP and NP. The previous impossibility result always goes in this way. For example, for CCLY21, you will say construct post-quantum zero knowledge does not exist unless NP is a subset of BQP. So one interesting about zero knowledge is we studied it because it has this close connection with computational complexity theory. However, if you just have CCLY21, you haven't really connected the computational class BQP and QMA. So QMA should be considered as a real quantum analog of NP, right? So our result is the first one establishes the formal connection. Also, before we establish this impossibility result, it's possible that with quantum communication we can somehow bypass the post-quantum lower bounds. For example, if you allow quantum communication, OT is actually in Q minicrypt. So this is this contrasts the LOCC setting or the classical setting. And also, if you allow quantum communication, any commitment scheme can be compressed into a non-interactive one. So there is also I think recently Lowen and his collaborators, sorry, I cannot memorize all the names. They also established that any interactive argument system can be compressed into a 3-round one if you are allowed to use the quantum communication. So all this evidence show that it seems once you allow communication, quantum communication, you can compress the interactive complexity. However, given this evidence, it's possible that you can also do the same thing for zero knowledge protocol, right? And our result just is the first one to tell you that no, there is a no go. This kind of quantum advantage will not happen to quantum ZK round complexity. Okay. Also, through the proof, we develop a sequence of quantum techniques to handle this inherent quantum nature of malicious verifiers. So these techniques we developed actually something quantum exclusive, deviating a lot from the previous paradigms. And I view this as a starting point instead of the end of the line research, because now we establish the impossibility for ZK. You could go further and ask, is there any possibility for concurrent quantum ZK, right? And other basically whatever simulation-based fully quantum protocol. I believe to prove impossibility lower bounds for those protocols, you're gonna use some of our tools. Because before this paper, there's no tools to handle this fully quantum setting. The most you can do is post-quantum setting. Okay. Now, today, I will introduce our technique. The outline goes as follows. First, I need to briefly recall the first or the best classical result, like the technique they used, Berkeley-Lindell back in 2002. We need this as a background. Then I will talk a little bit about post-quantum impossibility, showing like what's the new difficulty there and what did they do to take care of the problems. Now I'll go further to show the new challenges in the folding point setting and how we handle that. Yeah. So let me start by the classical lower bounds. So in this part, everything is classical. Okay. So we are proving a lower bound for zero knowledge. Zero knowledge says for any efficient verifier, malicious verifier, you should be able to build a simulator. If you are proving something lower bounds, that means we just need to find one counterexample. You just need to find one efficient malicious verifier so that you cannot simulate. Then you are done, right? So the Berkeley-Lindell approach built this malicious verifier in the following way. This malicious verifier will utilize a random function. The random function gives you like 1-bit output. Input could be of varying length. Input length could go from like 0 bits to C bits. C is the upper bound, but it will always output one single bit. And there is a parameter epsilon like related to this function. Now this looks like an oracle model because I treat this function as our random function as oracle, right? Through this talk, I will do so, but don't worry because once you know the number of queries the simulator will make, you can always replace such a random function by Q as independent hash, where Q is the number of queries the simulator could make. So let's ignore this small little difference. So now let me describe how this malicious, how Berkeley-Lindell construct this malicious verifier. So at the beginning of the protocol, let's say the verifier, the prover, honest prover sends the first message, first honest prover message. The malicious verifier they build is to query this random function at using the message P1 as input. Now, there are two possibilities. The function will either return 0 and 1, right? If the function returns 0, the verifier immediately abort, like output reject. This is the end of the execution. However, if the function returns 1, then the verifier continue in the following way. The verifier forwards this message to the V. The green V is the honest verifier. You assume it exists, the honest protocol. Give the P1 to the honest verifier and learn the honest verifier response V2 and forward it back to the honest prover. And then you just continue in this way. Every round, you query the oracle to decide if you want to abort earlier or not. If you do not abort earlier, you invoke the honest verifier. So in general, if you are at the S round, say your execution has progressed to the moment that P sends the S1 message, PI, then the verifier will send the prefix P1, P2, all the way to PI-1 to the oracle. If the oracle returns 0, the verifier abort immediately. If the oracle returns 1, we continue the execution. Okay. Yeah, I hope this gives you the clear picture how this malicious verifier V star was constructed by Berkeley-Lindell. Okay. Now I'm going to talk about the properties. This is just the syntax of the verifier. So what do they achieve using this verifier? I claim this is their main technical lemma. I simplified it a lot, but I just want to focus on the most related part to this talk. So there is a clever way to set the parameter epsilon related to the function h. Though this clever way is highly non-trivial, and I think there is a reason why they choose to do so. But due to the limit of this talk, I won't be able to explain that reason. But trust me that there is a clever way to set up this epsilon to achieve the following two effects. The first effect is if you set the epsilon to be if you set epsilon so that the oracle will allow you to continue the execution, because if you set the epsilon differently, it changes the probability of early aborting, right? Let's say if your early aborting doesn't happen too much, then you could achieve effect 1. That means the straight line execution, meaning that the execution between the honest prover and the verifier will successfully finish go through, finish, run the protocol until the end with some good probability, 1/poly. That means if you consider honest the interaction between the honest prover and the malicious verifier with this early aborting behavior, you can set the epsilon so that there are still like a 1/poly probability you will finish the execution. So this is the first effect they achieve. Here is an implication of this effect. If you achieve so, just simply by the ZK property, if you replace the prover by the simulator, you should also be able to make the output a accepting view with probability 1/poly, plus or minus negligible. It's just because whatever the honest prover can do, your simulator should also be able to do. Okay, so that's the first thing they achieve. Second effect, if you set the epsilon properly so that your random aborting happens often. So you can see that there are two directions. The first thing you don't want it to happen too much. And the second thing you want it to happen a lot. So a successful rewinding will never happen, almost never happen. Which means that if you reach a certain point of time, if you want to rewind the execution back and to see a new execution with high probability, you're gonna see early aborting. So this condition says you can only see the accepting transcript once. You cannot rewind it back and see another accepting transcript. This is a hard step, how they set up the epsilon. That's the thing I want to talk about. But I'm just telling you that there is a regime of the parameter epsilon to help you to achieve these two conditions simultaneously. Okay. Once you achieve the second condition, the second effect, there is the implication. The implication is if X is not in the language, if you evoke the simulator on the V star, it will almost never accept. So now I won't prove how to achieve effect 2, but I'll tell you, assume effect 2 is true. Why this implication is true, okay? The proof is simple. The simulator makes black box to access to the verifier V star, but this V star essentially is just the honest verifier with this oracle, deciding if you want to early abort or not, okay? So if the effect 2 is true, that means rewinding will happen with probably almost 0, okay? Then you can view this part as a malicious prover because there's no rewinding. You can just forward execution between the simulator and the honest verifier. You think this honest verifier is sitting externally. This is some honest verifier. Okay. Then by standard soundness, if X is false, such a verifier, external verifier, should reject, or it should accept with probably almost 0. That's the proof. Okay. Now look at these two parts. This is the BPP decider. What do I mean by that? If X is in the language, you have a machine that accepts with probably 1/poly. If X is not in the language, you have a machine that rejects with probably 1. So this is the BQP decider. By the way, the simulator is also PPT time. So basically, that's what Berkeley-Liang did.
Does epsilon depend on the runtime of the simulator?
Yes, it has a relation with the number of queries Q. Yeah, but you are proving lower bound, so you should say assume the existence of simulator. Then at that moment, you know the number of Q. Okay. So that's their paradigm. Okay. Next part is I want to tell you how CCLY extend this paradigm to a post-quantum setting. Okay. First of all, what's the difficulty? The difficulty is the simulator now can make superposition queries to the malicious verifier V star. So let's keep this in mind. First, I want to tell you that at the very high level, the CCLY basically following the same paradigm as the Berkeley-Liang, in the sense that they also build a BQP decider in the way shown in fair set, and their machine is almost the same, basically the simulator with access to malicious verifier. Also, their malicious verifier is using the same random aborting behavior with V star. Actually, it's not. There are slight difference, but at the for this talk, it's okay if you treat them as exactly the same. This is possible simply because CCLY is for the post-conf setting. In particular, the honest verifier V is still classical. Because it's classical, so you can build V star by like, sending the query to the oracle to decide to continue or not. All these things are consistent, you can do. Okay. But there's one problem. Like in the previous slide, I showed you two things. First, when X in the language, this decider needs output something like a step. This step for CCLY is still easy because like it's just implication of the ZK property. If your honest prover can do something, then simulator can also do something. That part is easy. What is difficult is the case of X not in the language. As I showed you in the previous slide, I need to build a malicious prover out of the simulator and then rely on the soundness of the original protocol to show that the BQP decider you build must output reject. So that is a hard step. Why it's hard? Because in this post-conf setting, simulator can send polynomial query, superposition queries to V star. However, the protocol itself is post-quantum. So if you think about this paradigm, the external verifier is honest. He's expecting to see classical messages. Here we can just forward what the simulator sent directly to outside, because this simulator is sending classical message because this is a classical setting. However, once you are in the post-conf setting, the simulator is making superposition queries. This P1 message in the post-conf setting is a superposition of a lot of messages. How can you send a single classical message to the external honest verifier? That's the main difficulty they face, or they were faced with. Okay. Now let's focus on that part, and I'll explain to you their main technical idea. Their main technical idea is as follows. This is the hard step they want to do: build a malicious P star talking to a verifier, honest verifier. The technique they use is actually most of you are familiar with. It's a measure and reprogram technique, which was originally developed in establishing the quantum security of Fiat-Shamir. So in this setting, the idea can be interpreted as this simulator. You run this, our malicious P star we are going to build, run the quantum simulator internally. I know in advance that the simulator will make a bunch of queries, Q queries in total. So the P star will pick randomly in advance K positions, 10 point, K 10 point. So this K 10 point, like once simulator send a message at that moment, the P star will measure that message. So pictorial is like that. Let's say the P star in this picture, this P star select this position and this position in advance randomly. Okay. Now the P star just started execution. When the simulator sends the first message, here I'm using this asterisk representing for wildcard symbol. It's just some superposition. I don't know its structure. I have no idea. However, at the beginning, this oracle is instantiated as always aborting oracle, meaning that no matter what you send to me, I always abort. Okay, so the first message from the simulator, like we don't need to respond because the oracle just always reject. Okay. If we do not respond to this message, the execution cannot go further. The simulator, the only thing simulator can do is keep trying this message again and again until the case, the green moment happens. At the green moment, again, this is a superposition of messages. Here, we measure this message to get a classical message P1. Simultaneously, we program the oracle to output 1 at this point, P1 only. At other points, still it's outputting aborting, but at P1, I change the oracle. It becomes output 1. Okay. And then we forward this out to the honest verifier. Verifier will respond with the corresponding verifier's message, and we forward it back to the simulator, and the execution continues. Interesting happens at the next query. Let's say at this moment, simulator sends another message. This message, the structure, again, I don't know. It's a superposition. However, I can always decompose it as, here I omit the coefficients, amplitudes, but it should be a superposition of P1, the point we opened, and everything else that is not P1. Okay. If I know it's of this structure, I know what to do, because for P1, that's the only position the oracle H is open. So for this one, that means this position I need to response. However, the response is deterministic. Previously, we learned from the external verifier that if you send me P1, I'm going to respond with you with V1. Because this is the post-quantum setting. Honest verifier is classical. It's deterministic if you fix this random tape. So if you give him P1, he always responds with you the same V1. So this part, this branch in the superposition, we know how to answer. It's always a V1. For everything else, the oracle is closed. The oracle is only open in position P1. So for everything else, you don't need to answer anything. It's bought. So the information I want to convey here is you can answer this purple-colored query without querying the external verifier, because you already have all the information you need. Okay. You just keep doing so. But I want to emphasize that I already emphasized that this relies heavily on the deterministic nature of classical V. Okay. Yeah. You just keep doing so. Yeah, I don't need to repeat. So now basically we build a approach. We have approach to build a malicious P star from the quantum simulator. This equation comes from the measure and reprogram lemma. You don't need to read all the detailed parameters. The only thing I want to say is the original execution between sim and verifier is totally quantum. Now I change the execution by select this random position and measure them. This kind of behavior will only decrease the winning probability of the simulator by a 1 over polynomial factor. So it won't affect the probability of the original game too much. That's why if the original simulator succeed with good probability, now you only have a polynomial drop in this measurement program. So this is enough for you to prove soundness. Okay. By the way, if you're interested, K, 2 to the power K, the K is number of rounds. Q is the number of queries simulator will make. So you can see we are focusing on constant rounds. So K is constant. So it's the 1 over poly drop. Okay. I guess this is another way to view, not another way to view, is another way to illustrate what I said previously. In my mind, when I'm working on this project, I always think it as I draw bars. Each bar represents a particular round. The job of the simulator is to go from the round 1 all the way to round, let's say if you have 3 rounds, this is round 3. Sorry, it's a typo, round 3. So before you open the oracle, for example, at the beginning, the oracle is closed. So your attempt to go down is always blocked until the green moment. You make a measurement, so you go through, reach the second round. Then rewinding queries is represented as the up arrow. Okay, you can think the execution is really jumping between these lines. Yeah, it shows pictureness. So the main idea of CCLI basically is using measure and reprogram technique and relying on the determinism of the honest verifier to get a way to simulate the queries. When you are simulating queries, for the rewinding queries, you only need to access the external verifier once in these things. Once you learn the response once, you don't need to learn it anymore to answer the same the queries for the same round. So that's essentially why you can build a straight line malicious prover, because your prover we are going to build don't have the ability to rewind the verifier. So you have to make it straight line. That's the main power. So there is another issue. Let me tell you the issue. The issue is the measure and reprogram techniques select these measurement points randomly at the beginning. So there's no guarantee that the first time you measure, you happen to learn the first round prover message. This is not guaranteed. But I don't have time to go to further details, but I can tell you that in the post-quantum setting, this is not the issue. Because the verifier is deterministic. So if you happen to learn at the first measurement, you learn the first 3 round message, sure, you just follow all of them one by one, because you know for sure that for any for the same query, the verifier will answer in the same way. So roughly that's the idea, but let's don't focus on too much on this point. Okay. Now let's go to our techniques. In our setting, as you can see, we want to do fully quantum thing, right? So the first obstacle is we don't even have a starting point. Both Barrock, Lindell, and CLY use this random aborting behavior to build the malicious verifier. That is possible because at least the messages transmitted between verifier and prover are classical. So you can apply a hash function on top of it to learn a bit to decide when if you want to go if you want to abort early or not. Here, if the messages are quantum, we don't even know how to do that. Also, if like somehow you recover this random aborting behavior by modifying the protocol a little bit, you know, the verifier in the quantum setting is inherently quantum. So the previous argument relies heavily on the deterministic nature of the verifier. Now, even if you can dequantize the communication, I don't think you can dequantize the nature of randomized nature of the malicious verifier. It's unclear if the previous argument can go through. Now, also as I explained earlier, we have these possibilities, like you can compress rounds of interactive protocols once you have a quantum interaction. Because of that, it's even unclear if we will succeed if we try to prove a lower bound. Okay. So our key idea is can be summarized as the following 3 ideas. The first idea is we can use the API pair between prover and verifier to dequantize the messages. Once you actually suffice to dequantize the prover's message. If you dequantize the prover message, you can recover the random aborting behavior using the previous technique. However, one thing I want to emphasize that is it's unclear if you are doing this, if you will succeed or not, because this is like just syntactically you recover the random aborting behavior. As I said earlier, the verifier is still randomized, it's still quantum. This is like inherently different from post-quantum setting. Even if you make it syntactically classical, the interaction is classical, but it's not guaranteed that you can reapply the previous techniques. So that is what I noted with red text. It's unclear if you are doing so. It's unclear if we really solve the problem or we push the problem somewhere else. Okay. So, but at least this helps us to pin down the issue to the intrinsic random nature of the quantum verifier. Okay. Starting from this point, we developed other techniques. I don't think I have time to talk too much about them. And also at this moment, when I explain these 2 techniques, it's unclear if you can understand it without looking at our full calculation. But I want to emphasize that from retrospective, these techniques looks like not complicated, but this is like more like deceptive. If you look at the analysis, all the difficulties pushed to the analysis. So now let me give you a little flavor of our analysis. So our malicious prover is built in the following way. Let's say this is the honest verifier. The verifier has registers P1, P2, P3. Let's say the 3-round protocol. This P1, P2, P3 is there to store the messages from the prover. We assume that they share API pairs. From now on, I won't talk about them explicitly. You should always assume that they have these API pairs. Because of that, I can assume their messages are classical by teleportation. Okay. Now, if the prover sends a message in a particular message register M, this M meaning that's a message register, people are exchanging this message using message register. When the verifier receives this message register, he just puts the message register in his internal registers and then swap this message to the correct place. For example, P1 is for the first message, so verifier swap the P1 for message M register to the P1 register, and then apply the honest verifiers algorithm to generate the first round verifier message row 1 in this M register. Okay, so and then send this M register back. That's our modeling. We did the register exchange between these 2 parties to carry the messages. Okay, that's how the honest verifier do, or how we model the honest verifier. So for malicious verifier, there are 2 modifications we did. First is the same as before. We have a random oracle H in the same way as in previous techniques. Now we have 2 counter register. One GL is called global counter. LC is local counter. I have these 2 extra registers. When the verifier sees the first message, the global counter gets added 1 automatically, always. We do not query the oracle for that. Just once you receive a message, you increase the global counter by 1. And then you start to query the oracle to decide if you want to board early or not. The remaining part is you only do that if local counter is laying behind by 1 compared with global counter. That's the technical condition. But the only thing I want to emphasize is every time you receive a new message, global counter always gets increased by 1. But whether if you will increase the local counter, it depends if you want to continue. If you do not earlier board, if you continue, then local counter get increased by 1. So in your mind, GL basically counts the number of queries the address make. Every time the simulator make a query, it gets increased by 1. Local counter is the indicator for where the execution really is. When you execute the execution successfully to round 3, then this local counter should be 3, even though adversary has already made 100 queries. But the actual execution only proceeds to round 3. That's how you should think about it. Yeah. These things are just like you increase the local counter and then it becomes like this. Okay. That's our model. So with this model, we can design something called a fake malicious verifier. This fake malicious verifier, V double dots, it's the same as V tilde, the malicious verifier we built. The only difference is it does not perform this step. This is the only step that involves the real code of the honest verifier. Basically, V double dot execute all the messages arrangements and also the counter management, but it doesn't really execute the honest verifier behavior. That's the only difference. So with this design, our main technical lemma is to show that all the rewinding queries of the V tilde can be simulated via this V double dot. So here I emphasize this rewinding queries. If a simulator makes a query at third round at the first time, we still forward out that message to V tilde using measurement program. But when you are doing rewinding queries, we can replace V tilde use V double dot. You will see how this helps. I'm running short of time, so let me give you a flavor like what we are doing now. Let's say if now I want to consider a rewinding query. Rewinding query here can be modeled as this V tilde is the malicious verifier's unitary. So a rewinding means that you apply V tilde dagger. Then S is the simulator's local operation. Simulator performs some local operation. You go up local operation and go down. That's the rewinding. Throughout this rewinding, let's say at the beginning, the simulator, the verifier's internal registers are like this. These are the message registers. These are the counters. This is a message register exchanged between these two parties. They transmit message through this. This S is a simulator's local operator, or local register. This row is the verifier's internal state. You don't need to memorize the meaning of this. I'll just show you the result. If you model the things in this way, by a derivation, I won't go through each steps in detail because I'm running short of time. I'll just show you that eventually you will have something called a good branch and a bad branch. So the only thing you need to focus is at the beginning, your states looks like this. After the execution, you rewind it back, simulator performs some local operation, and then you go down to the same round. All these registers, these are like internal registers of the verifier, won't change at all. The only thing changes is the simulator's local register, because simulator performed some task when the execution was rewinded back. This is something I call good branch. And also I have a bad branch. The bad branch, you don't need to care how ugly it looks like. The only thing you need to know is local register gets stuck one round back, because you rewind successfully, but when you go down for the second time, the local operator actually gets stuck there. It cannot go down anymore. So if you have this nature, I can compare it with this rewinding, one round rewinding with this V double dots. If you compare, if you do the calculation for V double dots, you will get a much similar result as a good branch branch and bad branch. If you contrast these two branches, I think that's the thing I want you to focus. Like if you run it once, if you are using the real V tutor, you will get this. If you use the faked V double dots, you will get this. They look very similar in the sense that both of them has a good branch and bad branch. In a good branch, they match each other. In a bad branch, they differ only at this honest verifier's rewinding operator. There is a technical reasons, but intuitively the reason is the V double dots differs only with V tutor by not applying the honest verifier's unitary. That was reflected in this bad branch only. For the good branch, like nothing happened. It's the same. So basically, using this observation, let me jump into this picture directly. You can prove that if you are going back and forth through like two adjacent rounds, every time you return back this purple triangle, every time you return back to the round K, let's say, you starting from round K, you rewind back to round K-1 and then go back to round K again. You can keep jump between these two rounds. Every moment you return to round K, the real the V tutor execution and V, sorry, this should be double dots. With V double dots, at these purple triangles, they always have the same good part. Their bad part is different, but only at in a controllable way, as I showed before. This tells you that at least they have good branch. And then it's important to note that the good branch determines your acceptance probability. Because eventually, if your local counter does not match, that is considered as a rejection execution at the end of execution. So the story is once their good branch match, these two executions have the same accepting probability. Yeah. Now, this is just an analysis for a single round. Through a very, very involved technical analysis with a lot of new technical difficulties, we can extend this to multiple rounds using a hybrid argument. Let's say if you have 3 rounds, eventually I want to prove that I want to replace all the V tutor by V double dots. So I will first replace all the V tutor in the first layer, keep the second layer the same. This relies on the analysis I showed you before. Like these two executions, they are good branch always match, but they are bad branch, they differ in a controllable way. And then you do that for the second, jump from H1 to H2, do that for the second layer. In hybrid 2, you already replaced all the V tutor by V double dots. What's the benefit of this? Because you only invoke the real honest verifier once for each round. Only these black errors. When you are going down for the first time, you need to query the honest verifier once. For all the other things you are doing with double dots, this is something you can simulate without querying the external verifier. So this picture basically represents a real straight line execution. If you have this execution, you can build. If you have this H2 execution, you can build a malicious verifier by just forwarding out one message for each round. So this helps you to recover the previous argument for soundness. As I said, there are a lot of technical difficulties I need to handle, but I don't have time to talk about that. I hope this gives you a high-level point of view how our paradigm works. Anyway, this is a 100-page paper, so I cannot explain all the technical details. Just for this high-level paradigm, I would be very happy to answer any questions you have.
Does anyone have questions? So I have a question.
Yeah.
I don't think I fully understood why, where the determinism was being used in the post-quantum proof.
Yeah.
It's quite far back.
At this moment, you measure P1 and you learn V1 as a response to P1. In the next query, this query can be decomposed as a P1 part and a non-P1 part. For the P1 part, since it's deterministic, you know that if the external verifier saw P1 again, it's going to answer with the same V1. That's why you don't need to query it twice. For example, at this moment, if the randomized, you need to query it again to learn.
So let's thank the speaker.